Hello everyone, welcome to Sulekha Physics classes. It is the most easiest way to learn all the concept of physics through this class. Hope you all are doing well. Today I am coming with next topic of this chapter, wave optics, that is diffraction of light. We will discuss each and everything in detail about diffraction of light. Okay, in the previous videos we already discussed about interference of light, right? And this diffraction of light is very similar to the interference of light. There is a large similarity between diffraction and interference. Both are a result of superposition of waves. You know already about superposition principle. So interference is a result of superposition of two wave fronts. Actually there are two wave fronts from the two sources, but here in case of diffraction we will discuss this one, that in case of diffraction there is only one source, and according to Huygens principle each point acts as a source of secondary wavelets from this one source, and these secondary wavelets from each point of the source form diffraction pattern. So let us start with today's topic, that is diffraction of light. Okay, you know one important property of light, that is rectilinear propagation of light. What is that? That light always travels in a straight line. When anything comes in the path of light, then what happens? Because it always travels in a straight line. So let us observe these two things. First one is, suppose there is a small aperture or opening. AB is a small opening or hole, aperture is there, and this S is a source of light, right? Now when light reaches to this small opening AB, then light passes through this one, this opening, okay, and you know light travels in a straight line, so light just goes like this one, and between these two regions A dash, B dash, illuminatory region is formed. Light reaches at this point, but when light reaches above A, like this point, whether it crosses it? No. And this side on the screen, beyond this above SA dash and below B dash, there is a shadow of these regions. This is geometrical shadow. It means light doesn't reach at this point, because light always travels in a straight line, does not bend their path. So in case of this small aperture or opening, illuminated region is formed at the center and geometrical shadow region is formed above and below the illuminated region, right? Now let us observe another this experiment, this small obstacle or aperture, right? This is a small obstacle or any opaque substance. When the light travels in all possible direction, reaches at this point AB, light does not cross this point AB, right? So when light reaches to this A point, just goes like this one, here B just goes like this one. Between these two regions, no light reaches between this A dash and B dash. So between A dash and B dash, geometrical shadow region is formed, and light above this A, light goes in a straight line, travels in a straight line and reaches in these regions. Above A dash and below B dash, illuminated region is formed, right? So you must remember this one, that in case of small aperture opening, illuminated region is formed at the center and geometrical shadow region is formed above and below the illuminated region. And in case of obstacle, shadow region is formed at the center, okay, on the screen, and above and below illuminated region is formed. Okay, so all this happens due to rectilinear propagation of light, right? But after discovery, it is observed that some amount of light reaches in the geometrical shadow region also. When and why, how light enters in this region, we'll discuss later on. Okay, so this geometrical shadow region is not completely dark. Some amount of light reaches in this geometrical shadow region also, like this one. Suppose this is opening, light goes in this one, in this way. Okay, so this is a screen. Light reaches in this region and in this region. These are only illuminated region, but after some time it is observed that light at this corners of this aperture AB, light enters in this geometrical shadow region also. Okay. So this geometrical shadow region is not completely dark. After this it is completely dark, but in this region, in this region some amount of light reaches. So at this, in this region, in this geometrical shadow region, some bright, dark, like this diffraction pattern is observed. Here also bright, dark, like this one. Diffraction pattern is observed in the geometrical shadow region. This central region is completely bright, but this geometrical region, some amount of light reaches in that region also. Light spreads in this geometrical shadow region and diffraction pattern is observed. Alternate bright and dark rings are formed. Right? Again, in case of this small obstacle also, suppose this is a screen, right? Source reaches at this point. So you know, above this and below this one, there is a illuminated region and this is geometrical shadow region, right? But it is observed that light, some part of light reaches in this region also. Okay. And here this central region is not completely dark. Some amount of light reaches in this region also, and hence bright, dark rings are formed in this geometrical shadow region. This bending of light in this geometrical shadow region is called diffraction of light, and this bending of light only takes place around the edges of this aperture, around the edges of this obstacle, and spread into the region of geometrical shadow. This is geometrical shadow region as bright and dark rings are formed. This is geometrical shadow region and here bright and dark rings are formed. There is not a sharp boundary between this illuminated region and geometrical shadow region. At the boundary there is a alternate bright and dark rings are formed, and this bending of light around these corners or edges of the aperture or obstacle, this is called diffraction of light. Okay, I hope you understood this one. What do you mean by diffraction of light? The spreading of light, the bending of light in the region of geometrical shadow, okay, around the corners of the aperture is called diffraction of light. And when this diffraction of light occurs, we do not observe this diffraction of light in our everyday life. Why? Actually, some criteria is there. The size of this aperture and the size of this obstacle should be in the range of wavelength of light used. And you know that wavelength of light is very small, in the region of 4000 to 8000 angstrom, right now, and this wavelength region is very small. So how we observe this diffraction we do not observe in our daily life, right? But one thing you observe that when the door is open at your home, when the window is open, light enters through that door or window, and you observe that it moves in a straight line. Why? Because the size of door or window is very large as compared to the wavelength of light used, so no bending takes place, no diffraction of light takes place. Diffraction or bending of light around these corners or edges only takes place when the size of this, okay, obstacle or aperture is comparable to the size of wavelength of light used, and that small size of aperture or this obstacle, I think it's not possible. Very small, because wavelength of light is so small. So how you observe this in our everyday life? But again, there is one example, diffraction of sound wave, because you know that wavelength of sound is very large. It is comparable to the size of window, door, wall, anything. So it just bending takes place because size is comparable to the size of obstacle or aperture. So bending of sound waves takes place and it reaches at all places. Diffraction of sound wave we can easily observe, but no diffraction of light takes place because its wavelength is very small. So diffraction of light is not observed at all places. This is diffraction of light. Now we will discuss in detail what is diffraction of light, what are different conditions when diffraction of light takes place, diffraction due to a single slit in detail. Let us start that one. Please note down this one. Take a screenshot. Okay. So now, diffraction of light. What is the definition of diffraction of light? The phenomenon of bending of light around the corners of small obstacles or apertures. Suppose this is a small, we already discussed this, a small aperture, right? So this is source, light goes in this way, this is a screen. So at this corner or edges, light moves in a straight line, but here also bending of light takes place. Light moves this way, light bends in this way. It is bending by some angle to the incident direction, right? And this bending of light around the small obstacles or apertures and is constantly spreading in the region of geometrical shadow. Which region it bends? It bends in the region of geometrical shadow. This is the region of geometrical shadow, and here only in this region bending of light takes place, and this is called diffraction of light. But it only takes place if the size of this AB is the aperture. The size of this aperture is of the order of wavelength of light used, and wavelength of light is very small. So the size of aperture should be very small to observe the diffraction pattern. Otherwise it will not observe. So this condition is very important. Size of obstacle or aperture is of the order of wavelength of light used. So I think it's clear. Bending of light around the corners of a small obstacle or apertures, and it's spreading in which region? In the region of geometrical shadow. This is diffraction of light, and it only takes place if its size is comparable to the size of wavelength of light used, right? Now this diffraction is of two types. One is Fresnel's diffraction, other one is Fraunhofer diffraction. What is this Fresnel diffraction? If the source and a screen are at finite distance, from where? Finite distance from the obstacle, right? If the distance between the source and screen from the obstacle, suppose this is obstacle, this one is source, and this is a screen. If the distance between this source and obstacle, okay, and this screen and this obstacle is very small, finite distance, then Fresnel diffraction is observed. And if the distance between the source and screen from this obstacle is at very small, then no lens is required to converge the rays. No lens is required, right? And one thing, if distance is small, then in this case a spherical wavefront is used. A spherical wavefront. But in case of Fraunhofer diffraction, here source and a screen are at larger distance from the obstacle. obstacle. So in this case, Fraunhofer diffraction is observed, and if the distance between this source and screen are very large, then in this case lens is required to observe the diffraction pattern. Lens is required, and here incident wavefront is parallel. Because distance is large, so incident rays and incident wavefront is parallel. Here distance small, so incident wavefront is spherical wavefront. So these are two different types of diffraction. In your syllabus, we will discuss only this Fraunhofer type of diffraction, where the source and a screen are kept at very large distance from the obstacle. And in your syllabus, not it's given Fraunhofer just diffraction due to a single slit, but that diffraction is of Fraunhofer type. It means source and screen are at larger distance. So please take a screenshot of this one. And with this, I am going to end the class. In the next video, we will discuss about diffraction at a single slit. Till then, students, please keep revising and stay tuned with this channel. Thank you.